Hello everyone, my name is Renfei. Today I will introduce our work, Tight Bounds for Classical Open Addressing. This talk will have two parts. In the first part, I will introduce the definition of classical open addressing and also our results in the paper. The second part will be about a key subroutine of our final data structure. It is called rainbow cell and it plays an interesting role in the final construction. Let's start with the hash table problem. The hash table problem requires us to design a data structure that stores n keys out of some universe. The key set is dynamic, that we need to support insertions, deletions, and membership queries. The query can ask whether a key X is present in the current set or not, which will support those operations efficiently. This simple problem has a lot of applications in both the theory side and the real-life applications. And in the long history of hash tables, there's been hundreds of algorithms that can complete this simple task. And among them, there's one category of algorithms that is especially important, which we call the classical open addressing. So it is a very wide class of algorithms that it includes almost all of the hash tables that we have learned from the textbooks, and also basically all of the hash tables that were implemented for real-life usage. So examples include linear probing, quadratic probing, cuckoo hashing, double hashing, and many others. So these examples have two common properties, which form the definition of classical open addressing. The first property is that the entire hash table is just an array of several slots. Within each slot, we can either store one of the keys in the current set or just leave that slot to be empty. And this array is the only storage space that a hash table can access to, which means that the hash table is not allowed to create other additional storage for metadata. And also, when some slot is empty, it is just wasted, and the hash table is also not allowed to put other information into that empty slot. So this is the first property. And the second property says that each key X is mapped to a probe sequence of slots, namely S1, S2, and so on. Each of the entries in the sequence is one of the M slots in the array. And this sequence should be fully determined by the key X itself, the size of the hash table, and some random bits. Once this sequence is fixed, when we query the key X, the query algorithm is forced to probe the slots along the sequence, in the order that the probe sequence specifies. It must first probe S1, and then S2, and so on, until at some moment, the hash table is able to conclude that either X is already found or X does not exist. So once a hash table satisfies these two properties, we call it a classical open address hash table. Let's see some examples. The first example is linear probing. It is one of the earliest hash tables in the history. In linear probing, every key X is mapped to a random location in the array using a hash function h of x. When we insert the key X, the hash table will find the first empty slot at or after the location hx. As a result of this rule, when we query a key X, it will also first probe h of x, and then h of x plus 1, and then plus 2, and so on. This sequence is only depending on x, but not other things. So this satisfies the definition of a probe sequence, and therefore linear probing belongs to the class of classical open addressing. Our second example is uniform hashing, which instead of going to hx plus 1 and plus 2, it uses a sequence of independent hash functions h1, h2, etc. to map x to different locations. When we query a key x in uniform hashing, it will first probe h1 of x, which is a random location, and then h2 of x, which is an independently random location, and so on. Although this probe sequence seems more random than the previous example, but since this sequence is still fully determined by x and some other random bits, so the uniform hashing also satisfies the condition of a classical open addressing. And finally, let's see some example that does not belong to classical open addressing. Let's start with linear probing. There's one simple improvement that we can do over linear probing, which is that by rearranging the elements within the array in an appropriate order, we can maintain the invariance that the hash values of the elements in the array are increasing from left to right. Maintaining this additional feature does not change the time complexity of insertions and deletions, but since now the hash values are increasing, it enables us to use binary search when we query something. This will significantly improve the query time complexity. However, on the other hand, as we integrate binary search into our query algorithm, this does not belong to classical open addressing anymore, because in the binary search, we will first probe one of the slots and check if the hash value within that slot is too large or too small, and this will decide whether we go to the left or go to the right. So there is no prefixed probe sequence in advance, so this does not belong to classical open addressing. Now we have seen the definition of classical open addressing, and for this category of algorithms, the most natural question to ask is that what is the best time-space trade-off that we can achieve using any classical open address hash table? In this question, the space efficiency is measured by the load factor, which is the percentage of slots in the array that are actually utilized to store keys instead of being wasted. In the rest of this talk, we will use 1 minus epsilon to represent this quantity, and you can see that the smaller epsilon is, the better space efficiency we have. The time efficiency is measured by the expected time for each operation. Here we care about the slowest among insertions, deletions, and queries. So the basic question is asking what is the best possible relationship between the space efficiency and the time complexity. There's a lot of work studying this question, and over all of them, the best known time bounds that we have so far is epsilon inverse time per operation versus a load factor of 1 minus epsilon. So here, the epsilon inverse time means the slowest between updates and queries. There are some sophisticated techniques such that although the update time is still epsilon inverse, which is not improved, but they can make the queries much faster, up to log epsilon time. Log epsilon inverse time. So along this line of research, the current big open question is that whether there exists a solution that can achieve little o of epsilon inverse for both updates and queries. So our first result in this paper answers this question. We constructed a classical open address hash table that has log epsilon inverse update time and constant query time in expectation, when the load factor of the hash table is 1 minus epsilon. This does not only resolve the previous big open question, but also this is a doubly logarithmic improvement compared to the previous result. As a special case, when the load factor equals 1, which means that all of the slots within the array are utilized to store keys instead of being empty, we can achieve a operational time of log n. Our second result extends the construction of hash table to support dynamic resizing, which means that when we insert keys to the hash table or delete keys from it, we change the number of keys, and then the hash table will dynamically adjust the size of the array, either extending it or shrinking it, to keep the invariant that the load factor always equals 1 minus epsilon. With this additional feature, it does not change the space and time guarantees of our hash table. Our final result is a matching lower bound. It says that any classical open address hash table should incur log epsilon inverse time for these operations when the load factor is 1 minus epsilon. This means that our hash table is optimal, and this completely resolves the basic question for classical open addressing. So in the second part of the talk, let's introduce a little bit about rainbow cell, which is a key subroutine of our final construction. A rainbow cell is a classical open address hash table that stores n keys within n slots, which means that the load factor equals 1. What's special about this hash table is that it optimizes the update time over the query time. For updates, it only takes constant expected time to complete, but for queries, it is much slower. It takes n to the 3/4 time expectation. One funny thing is that since now queries are slower than deletions, we require the user, when he deletes a key, he should not only specify which key he would like to delete, but also specify the location of that key, because otherwise the hash table will not be able to even find that key that we need to delete. So this is the goal of a rainbow cell, and this picture shows the structure of it. The n slots in the array are partitioned into n to the 1/4 buckets. Within each bucket, there are n to the 3/4 slots in total, and the top root n slots are special. We call them the sky slots. And for each key in the universe, we assign one of the two colors to it using a random hash function. It is either a light key or a heavy key, represented using blue and red points in the picture. For those two colors of points, we have different rules to store them. For a heavy key x, it is further hashed to one of the buckets using a second hash function h of x. Then we require that x must stay in the correct bucket that it hashes to. But this is the only constraint that we have for x's location, and within that bucket, any slot will be a valid location. For light keys, we require that it must stay in one of the sky slots of any of the buckets. So as a result of these two rules, we can observe that all of the non-sky slots, which means the slots at the bottom, are fully occupied by the heavy keys, because light keys are not allowed to occupy those slots. At the same time, due to our design of probabilities of light keys versus heavy keys, we can conclude that in the sky slots within each bucket, half of the keys are light and half are heavy in expectation. So this is the structure of a rainbow cell, and based on this structure, it is rather straightforward to design all of the operations. Let's begin with queries. When we query a key, we can first see whether the key is heavy or light. If it is heavy, then we can see that it is hashed to one of the buckets, and if x is present, it must appear in that specific bucket. So our strategy is simple. we just scan through all of the slots within that bucket, h of x, and try to find x. This takes into the 3/4 time. And when we query a light key x, we know that x must stay in one of the sky slots. So again, we scan through all of the sky slots in all of the buckets, and then try to find x. This also takes into the 3/4 time. Now let's move on to deletions. Let's say that we are going to delete an element x from here. By simply taking x away, we have produced a bubble, which means it is an empty cell. And then, for the convenience of subsequent operations, we would like to move the bubble up to the sky slot area. In order to do this, we need to find some heavy element that we can pull down to the previous bubble. This heavy element is found by random sampling because we know half of the elements in the sky slots are heavy. So the sampling will complete within constant time. After we find such a heavy element, we move it to the previous bubble so that the new bubble appears in the sky slot area, and we are done with deletions. Since we have promised that the load factor of the rainbow cell should always equal 1, so after each deletion, there must be a subsequent insertion to fulfill the previous bubble. Let's say we're going to insert another element y that is also heavy and is hashed to this green bucket. Similar to the deletions, in order to successfully insert y, we would like to first move a light element to the previous bubble, which is in the sky slot of another bucket. Finding the light key can also be done using random sampling in the sky slots within h of y. And after we find such a light key, we can move it to the previous empty slot so that the new empty slot appears in h of y. And the last step is to insert y to the empty slot to complete the insertion. So far, we have introduced the operations of rainbow cell, and in the last few minutes, let me tell you how the rainbow cell can help our construction of hash table. Our final construction will be based on a tree structure, which every node of the tree will contain a rainbow cell of different sizes. The tree has several properties. First of all, when you go down to lower levels of the tree, the nodes become significantly smaller. But at the same time, the tree will be wider such that there are a lot of nodes at the same level. So as a net effect, most of the keys will be stored in relatively low level nodes, where the rainbow cells are very small. When we query a key x, it is very likely that key x is staying in one of the very small rainbow cells, because most of the keys are. So even if the queries of rainbow cells are very slow with respect to the rainbow cell size, but the rainbow cells are very small, so the queries are expected constant time. The updates are another story, that when we perform updates in the hash table, our algorithm will require us to kick elements along a path from the root to some internal node. This will perform insertions and deletions to the rainbow cells for a sequence of relatively large rainbow cells. But insertions and deletions of rainbow cells are very fast. They are constant time. So our updates are also very efficient. So that's all about my talk. Thank you.